Good afternoon, class. We're looking at chapter 2, limits, section 2.4, limits, algebraic methods. We have looked at limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits, algebraic methods. So here's the synopsis of what we covered. Finding limits by numerical and graphical methods, limits of functions at finite numbers. The definition is, the way we read this, the limit of f of x as x approaches a equals L. The limit of a sub n as n approaches infinity equals L. We say that the a sub n converges to L. If the limit of a sub n as n approaches infinity is infinity, or negative infinity, or does not exist, we say the sequence diverges. And to find limits, basically plug in and observe. We are interested in finding the limit of f of x as x approaches a for all these graphs. And so as we approach a from the left and right, the graph moves this way from the left, this way from the right, and along the y-axis from the bottom, from the top. The limit in all three cases exists, and the limit of f of x as x approaches a equals L. What's the difference? In this case, f of a is L. In this case, f of a, we have a hole here, is something else, b. In this case, f of a is not defined. We have a hole here, we don't have a solid point. So in short, in part A, f of a is L. In part B, f of a is b, which is not equal to L. In part C, f of a is not defined. But in each case, regardless of what happens at A, the limit of f of x as x approaches a equals A. Definition of a horizontal asymptote HA is as follows. If you have the function y equals f of x, the line y equals L represents the horizontal asymptote if the limit of f of x as x approaches negative infinity or positive infinity is L. Vertical asymptote, short VA, has the equation x equals a if the limit of f of x as x approaches a, or a from the left or a from the right, is either positive or negative infinity. And a limit exists if one-sided limits are identical. In other words, the limit of f of x as x approaches a from the left equals L, and limit of f of x as x approaches a from the right is L, then we can say the limit of f of x as x approaches a equals L. And now section 2.4, limits, algebraic methods. I'm going to remind you of limit laws we discussed in the case of the sequences. So let f of x and g of x be defined for all x over some open interval containing a. Assume that L and M are real numbers such that limit of f of x as x approaches a is L, and limit of g of x as x approaches a is M. And let C be a constant, a number. And then each of the following statements holds. The sum law for limits. The limit of f of x plus g of x as x approaches a is the limit of f of x as x approaches a plus limit of g of x as x approaches a, or L plus M. In other words, the limit of the sum is the sum of the limits L plus M. Difference law for limits. The limit of the difference is the difference of the limits L minus M. Constant multiple law. The limit of C times f of x, if you as x approaches a, if you multiply it by constant, you can take the constant out. C times L. The product law. The limit of a product is the product of the limits, and it's L times M quotient law. The limit of a quotient is the quotient of the limits, L over M. Needless to say, as always, the denominator can't be zero. The power rule says the power law of limit. The limit of f of x to the power of n as x approaches a is equal to the limit of f of x as x approaches a to the power of n, or L to the power of n for positive integer n. And the root law says the limit of the nth root of f of x as x approaches a is the nth root of the limit of f of x as x approaches a, or the nth root of L for all n, for all L if n is odd, and for L larger than or equal to 0 if n is even. I want to make sure we understand what's happening here. If you happen to have an odd root, for example, cube root of 8 is 2, cube root of minus 8 is minus 2, we don't have a restriction. However, square root of 4 is 2, but square root of minus 4 is not a real number, or it's 2i, where I, by definition, is square root of negative 1. So that's why we have this restriction here. Also, the direct substitution property that we have already discussed, a continuous function at a has the following limit value. The limit of f of x as x approaches a equals f of a. This is the limit. This is the functional value. Let's look at this example, and we are going to apply the limit laws on that first. That means we are going to cut this, the limit of x squared minus 3x plus 7 as x approaches 4. We're going to cut this into 3 terms, and therefore we take the limit of each term. So the limit of x squared as x approaches 4 plus the limit of minus 3x as x approaches 4 plus the limit of 7 as x approaches 4. This one, we use the power rule. This one, we use the constant rule. We take the negative 3 out, and this is a constant. So this one is limit of x as x approaches 4 quantity squared. And this is where you can replace the x with 4. When you get to this expression, you can replace it. Same thing here, and this is a constant. So we get 4 squared minus 3 times 4 plus 7, meaning 16, minus 12 is 4, plus 7 is 11. However, we had mentioned before that you can simply plug in, and if you do so, you get to the same answer. The easy way out is to plug in and see whether you get an answer, or it's an indeterminate form that requires more work, meaning you use your algebraic techniques. We want to evaluate the following limits if they exist. We are given a graph, and we are asked to come up with the limit of f of x plus 5 g of x as x approaches negative 2. Dealing with the graph, we use the limit laws to cut them into 2 pieces. Limit of this piece plus 5 times the limit of this piece, where f is the purple, the red function, and g is the blue function. So we need to find each piece. So the very first thing is to find limit of f of x as x approaches negative 2. This is negative 2 along the x-axis. If we approach it from the left of that, we are moving this way. If we are approaching it from the right of negative 2, we are moving this way. In both cases, we are moving towards this hole. We never get there, but that's the concept of a limit, giving rise to the answer 1. We want to find this piece, limit of g of x as x approaches negative 2. So going this way from the left, going this way from the right, both of them is moving towards this point, which has a y coordinate -1. And so we plug in, we get 1 plus 5 times -1. They add up to negative. The limit of f of x times g of x as x approaches 1. Again, we do the limit laws and we separate them into the following: limit of f of x as x approaches 1 times limit of g of x as x approaches 1. And we try to find each piece. First, we want to try to find limit of f of x as x approaches 1. And remember, the f function is the red function. Here's number 1. From the left of number 1, we move this way. From the right of number 1, we move this way. And in both cases, we are moving towards this point, which has a y coordinate 2. So the limit of f of x as x approaches 1, doesn't matter from the left or right, is the same. The limit does exist, and it's equal to 2. What about this piece? The limit of g of x as x approaches 1 does not exist. The question is why? Well, from the left and right of 1, we are looking at the blue graph. So from the left, we are moving this way, which means we are moving towards this point, and it has a y coordinate -2. From the right, we are moving this way. We are moving towards this point, and now it has the y coordinate -1. Because the two are not identical, the limit of g of x as x approaches 1 does not exist. And because one of them doesn't exist, the product doesn't exist either. The limit of f of x times g of x as x approaches 1 does not exist. DNE. You can also look at it from the point of view of one-sided limits here. In other words, the entire limit instead of looking at g of x. So you can write the limit of this expression as x approaches 1 from the left and then 1 from the right. 1 from the left, that means each one of those from the left. Now this one, the limit of f of x as x approaches 1 from the left or right makes no difference. From the left and right, they're identical. So this is 2, but this one from the left is -2, the product of 2 and -2. -4. Same thing now from the right. So from the right, again, each one from the right. This one from the left or right makes no difference. So this is 2. But from the right, now this one has a different value, -1. So you multiply these two numbers, everybody, 2 and -1. And therefore, the limit of this function as x approaches 1 from the left and one from the right are different, the limit does not exist. This is a different way of approaching it. Both of them, of course, they give us the same result. Now, to make sure we understand the concept, I want to add a couple of things. And one of them is, okay, what is f of -2? Because I want to make sure you understand the difference between a functional value and a limit. Limit says when we get closer and closer to that point. Functional value says precisely at that point. So at x equals -2 for the red or purple function, you're looking for a solid point. So -2 is here as far as the x is concerned. So you look for a solid point, which is this guy, and it has a y coordinate of +2. What about g of 1? Again, we are looking at the blue function. Here's number 1 along the x-axis, and we are looking for a solid point for the graph of the blue function. Here's the solid point, which has a y coordinate -2. So we want to distinguish between the limit and a functional value. The limit of absolute value of x over x does not exist. Why is that? Because of this one-sided limit. So let me remind you of the definition of an absolute value of x. Recall, absolute value of x is x. If x is larger than or equal to 0, minus x is if x is less than 0. I want to make sure we understand this doesn't mean a negative number. In fact, it's the opposite. So the idea is that this means the opposite. So if you are looking at, for example, 5, you know the answer is 5. But what about -5? Also, the answer is 5, but you are here, and it means write the opposite of -5, which is still +5. So I want you to understand the concept. Now, the function f of x is absolute value of x over x, this function. If x is larger than 0, this can be replaced with x divided by x is 1. And if it's less than 0, this can be replaced by minus x over x becomes -1. And this has the equality. This one doesn't, because you're looking at a function with the denominator x. Denominator can't be 0. So this part, this is a piecewise defined function. The top part, y equals 1, is a horizontal line, but it says x is larger than 0. So it starts from here and moves on, and there's a hole here that is not covered. On the other hand, this function is the horizontal line y equals -1, but it's for x less than 0, so to the left of 0. As you can see, the limit of this graph or function, the limit of absolute value of x over x as x approaches 0 from the left, we move from the left. We never get there, but we are moving towards this point that has a y coordinate -1. However, the limit of absolute value of x over x as x approaches 0 from the right, we are moving this way, and the y coordinate is 1. Therefore, the limit of absolute value of x over x as x approaches 0 does not exist, because one-sided limits are not identical according to this. The limit of f of x as x approaches a from the left and right are identical. The limit of f of x as x approaches a does exist, and it's equal to L. In this case, they have two different answers. The limit does not exist. We want to find the following limits, and all you have to do, plug in. So what do we get when we plug in for the numerator? What do we get for the denominator in the square root, in the root function? If we plug in 2, we get 4 times 2, 8 plus 1 is 9, 3 times 2 minus 2 is 4. And that's 3/2. In other words, you plug in and it works out. The limit of 1/4 plus 1 over x plus 4 as x approaches -4. What do we get if we plug in class? If you replace the x with -4, you get 0 over 0, which is an indeterminate form. Remember that. Which means, in essence, more work, you have to use your algebraic technique. What we are dealing with here is a complex fraction. And you have to change it to a simple fraction using LCD, the least common denominator. You have two fractions in the numerator, 1 over 4 and 1 over x. Their LCD is 4x. You are going to multiply and divide by 4x. It's important to understand it is the 0 in the denominator that we are trying to get rid of. As a result, you never distribute. You just keep the bottom as a product, but you do distribute the top, which means if you multiply 4x by 1/4, you get x. You multiply it by 1 over x, you get 4. And notice now, we were hoping that we get the same factor of x plus 4 so we can get rid of it. And now we can. And the limit of 1 over 4x as x approaches -4, if we replace the x now, we get -1 over 16. To determine LCD, you look at all fractions that you have. So this is one fraction. This is another one. There's nothing else. So this is the main fraction bar. Sometimes you may have fractions in the denominator as well. So for 1/4 and 1 over x, you're looking for LCD. You don't find anything in common between the two denominators, therefore their product is the LCD. If there is anything in common, you don't want to repeat that. What about this one? The limit of x squared minus 25 over x squared minus 5x as x approaches 5. If you plug in, you get 0 over 0, also indeterminate. And because this is a rational function, the technique is to factor. Over here, it was LCD. And of course, one thing I want to add that will help you see the answer, when x approaches 5, that means this must have a factor of x minus 5. If x is approaching negative 5, then it must have a factor of x plus 5. If x is approaching 2, it must have a factor of x minus 2. So that will help you with the factoring. Of course, the denominator is very easy. You have x squared minus 5x. All you have to do, take the x out and you get x minus 5. The numerator, you can replace the 25 with 5 squared. So you can see a squared minus b squared is a minus b, a plus b, which gives you x minus 5, x plus 5 in any order. So we can factor it in the following manner. The common factor of x minus 5 is dropped. We get limit of x plus 5 over x as x approaches 5. And when we plug in, we get 10 over 5, which is 2. So it's pretty straightforward, everybody. A quick recap of this page. You plug in, it works out, you're done. You plug in, you get some sort of an indeterminate form, in this case 0 over 0. Because you have a complex fraction, LCD is the answer. Over here, when you get a 0 over 0, it's a rational function. Factoring is the answer. Do the factoring, and again, notice it's 0 over 0. The technique is factoring. X is approaching 4. So that means there must be a factor of x minus 4. The top is easy. You take the x out. The bottom, you want two numbers. The product is negative 4. The sum is negative 3. So we get negative 4 and positive 1. So we have the limit as x approaches 4 of x times x minus 4 over x minus 4 times x plus 1. Common factor of x minus 4 is dropped. And if we plug in 4, the final answer will be 4 over 5. In this case, whenever we have a square root, first of all, we plug in, we get 0 over 0. If it works out, we are fine. If not, we have to use the proper technique. In this case, the proper technique is conjugate. And this is a minus b. Its conjugate is a plus b. Which is square root of 1 plus h. Let me actually. And then plus 1. We multiply and divide by it. The product is a squared minus b squared. So over here is the square root of 1 plus h. Quantity squared minus 1 squared. Now, as far as the denominator is concerned, again, remember, it is 0 in the denominator, which is bad. We want to get rid of, so we are hoping to get rid of that. You never, ever distribute. So you keep the product in this format. This one, this comes out, becomes 1 plus h, and this is 1. So minus 1. 1 and minus 1 cancel each other. H cancels out the h. And now if you plug in 0, it becomes square root of 1, which is 1, and 1 is 2. So 1 over 2, or 1/2, is the final answer. We do the same thing here. We plug in. Negative 4 u squared becomes positive 16 and 9. 25 comes out as 5 minus 5 is 0. Negative 4 and 4 is 0. So you're looking at 0 over 0. It's an indeterminate form because the numerator is in the form of a square root here. We multiply by its conjugate, which means we change this to a plus 5. We multiply and divide by that. We keep the bottom as a product. The top becomes square root of x squared plus 9 quantity squared minus 5 squared, which becomes x squared plus 9 minus 25. We can combine these two numbers into negative 16. Notice we haven't touched the denominator, and we can replace the 16 with 4 squared. So we are looking at a squared minus b squared, which is a minus b, a plus b. So the numerator is x minus 4, x plus 4. Because remember, even if we go back to the original one, x is approaching negative 4, makes the denominator 0, and we are hoping to get rid of that. We just found a way to get rid of it. And so we do so. So now it's the limit as x approaches negative 4 of square root of x squared plus 9 plus 5. We are going to plug in. When we do that, minus 4, this one, you square it, you get 16. I mentioned that before here. 16 and 9, they add up to 25. And so this comes out as 5. So you're looking at minus 8 in the numerator and positive 10 in the denominator. And the final answer is negative 4 over 5. That's the final answer, everybody.